Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
Science in Easy English.
What is happening to Earth's core?
And we are just incredibly thrilled to have you joining us today for this deep dive. Our mission for this session is, well, it is massive.
It really is.
We are taking a huge stack of cutting-edge geological research, brand new seismic data, and recent scientific articles.
A very tall stack of articles.
Yes, exactly. And we are going to use all of it to try and understand the wild, unseen world operating 3,000 miles right beneath your feet.
Because when you walk outside, you usually think of the ground beneath you as solid, dependable, and
Yes.
totally unchanging.
Right, you just assume the Earth is completely stable.
But the data we are digging into today reveals a completely different reality. The center of our planet is behaving in bizarre, unpredictable ways.
It's shifting.
Shifting, slowing down, reversing direction, and even existing in states of matter that sound like they belong in a science fiction novel.
Okay, let's unpack this. Because to really grasp how weird things are getting down there, we have to look at the massive anomaly that started this whole investigation. Let's just break down the Earth's basic structure for you really quickly.
Right, so you have the wafer-thin crust, we live on the thick hot mantle, the liquid outer core made of iron and nickel.
And then the inner core, which is roughly the size of the moon and heated to temperatures rivaling the surface of the sun.
So for decades, seismologists have been using earthquake vibrations, specifically shear waves, to study that inner core.
But there was a glaring problem with the data they were getting right.
A huge problem. These waves were moving way too slowly through the center of the Earth. Given the crushing pressure and extreme heat down there, the inner core should behave like an incredibly dense, rigid sphere of solid steel.
But the seismic readings suggested it was bizarrely soft. The density and behavior resembled something closer to butter.
Which makes no sense for solid iron.
Right. And since we obviously cannot just drill a hole 3,000 miles deep to take a physical sample, how did we finally figure out what was going on?
That is where a groundbreaking study from researchers at Sichuan University and the Chinese Academy of Sciences completely changed the game. Because if you cannot go to the core, you have to recreate the core in a laboratory.
Which I imagine requires some extreme high-pressure physics.
Absolutely. You can't just put a piece of iron in mechanical vise to get core-level pressures. The researchers had to use dynamic shock compression.
I mean, what exactly?
They utilized a high-velocity projectile system, essentially a massive, highly specialized gas gun, to fire an iron-carbon pellet at an astonishing 4.3 miles per second.
Wow.
And when that projectile hits its target, it creates a momentary shock wave that subjects the material to a pressure of 140 gigapascal
That is wild.
and temperatures spiking over 4,200 degrees Fahrenheit.
That is just an unfathomable amount of kinetic energy to unleash in a lab setting. But what actually happens to the iron and carbon in that tiny fraction of a second?
What's fascinating here is the discovery they made completely rewrites our understanding of high-pressure physics. They found that under those specific conditions, the inner core isn't a normal solid at all.
It's something else entirely.
Yes, it transitions into what is known as a superionic state.
Superionic. It sounds incredibly futuristic, but what does that actually mean for the structure of the metal?
Well, in a standard solid metal, all the atoms are locked into a rigid grid. But in a superionic state, the material is essentially having an identity crisis between being a solid and a liquid.
An identity crisis.
Exactly. The heavier iron atoms stay put. They lock together to form a highly structured, rigid lattice, a solid framework. But the lighter elements mixed in, specifically the carbon atoms, do not lock into that grid.
They stay loose.
The heat and pressure excite them so much that they detach from the crystalline structure and zip freely through the empty spaces in the solid iron framework. They behave exactly like a liquid.
That perfectly explains the seismic anomaly. It's like well, imagine a highly organized square dance.
I really like that analogy from the sources.
Yeah, the iron atoms are the dancers holding their positions in a strict, rigid grid. Meanwhile, the carbon atoms are like little kids running wildly through the gaps between the dancers.
Moving dynamically like a fluid.
Right. While the dancers remain a solid structure. That unique combination creates a material that is structurally solid but acoustically soft, which is exactly why those earthquake shear waves slow down when they hit it.
And that carbon isn't just some random impurity down there. It is the fundamental reason the inner core exists in its current form.
How so?
A major study from the University of Oxford investigated how the inner core even managed to freeze into a solid in the first place. Their computer simulations revealed a massive problem with pure iron.
Because pure iron wouldn't just freeze normally at those pressures.
Exactly. If the core were entirely pure liquid iron, it would have required an extreme amount of supercooling, dropping roughly 800 to 1,000 degrees Celsius below its standard freezing point, just to initiate the crystallization process.
Wait, if the core had to drop by 1,000 degrees just to start freezing, wouldn't that mean a massive sudden flash freeze once it finally hit that threshold?
Precisely. The inner core would have grown massively and erratically. That rapid, chaotic freezing process would have severely disrupted the convection currents in the outer core.
Which would have completely destroyed Earth's magnetic field.
Right. But the Oxford researchers discovered that adding a very specific amount of carbon, exactly 3.8%, acts as the ultimate cosmic antifreeze.
Cosmic antifreeze.
It alters the thermodynamics just enough to allow the iron to crystallize slowly and steadily with much less supercooling. So that 3.8% carbon is the secret ingredient that allowed the solid core to form without shutting down the magnetic field.
So if the carbon is acting like a flowing fluid inside this superionic iron lattice, does that change how the entire core moves as a massive sphere? Because movement is where this story gets even wilder.
It really does.
Back in the 1990s, the scientific consensus was pretty settled on a concept called superrotation. The idea was that the inner core was spinning just a little bit faster than the rest of the planet.
That was the accepted model for decades. But recent data analyzed by researchers from the University of Southern California and Peking University has completely upended that consensus.
They looked at a lot more data than the earlier studies, right?
A massive trove of seismic data spanning decades. Specifically, they focused on repeating earthquakes known as doublets, originating from the South Sandwich Islands between 1991 and 2023.
And didn't they also pull data from old Cold War testing?
Yes, historical seismic readings from old Soviet nuclear tests conducted back in the 1970s.
Using old nuclear bomb tests as a sort of geological sonar is such a clever scientific pivot. But how exactly do repeating earthquakes and old bomb tests prove that the core is changing its spin?
It comes down to the pathways those seismic waves take. A doublet is essentially an earthquake that happens in the exact same geographical location with the exact same starting mechanics, just years or decades apart.
So the waves travel the exact same route.
They travel all the way through the Earth, piercing the inner core,
Yeah.
and are recorded by detectors on the other side. Now, if the inner core was rotating perfectly in sync with the Earth, the seismograms from a doublet in 1991 and a doublet in 2023 should look completely identical.
Because the wave went through the exact same medium,
Exactly.
but they didn't look identical. The waves shifted.
By tracking how those waveforms systematically changed over the decades, the researchers could measure the exact movement of the inner core, and they discovered that its rotation has dramatically slowed down.
Slowed down by how much?
Well, right around the years 2008 to 2010, the core's relative rotation effectively paused. It matched the rotation of the surface perfectly.
Wow.
And since then, it has actually started backtracking. It is subrotating, meaning it is now moving slightly slower than the Earth's crust and mantle.
Wait, if the core is backtracking, shouldn't we feel that? Shouldn't the Earth's surface be grinding down due to the friction of this massive iron ball dragging inside it?
To connect this to the bigger picture, this is not some apocalyptic scenario where the Earth's engine is failing. The data from the Soviet tests help prove that this is just a natural multi-decadal cycle.
A cycle that repeats.
Yes, the core naturally oscillates, speeding up and slowing down in a rhythm that takes roughly 70 years to complete.
So it's swinging back and forth.
Exactly. The last time the core hit a major turning point and reversed its relative direction like this was back in the early 1970s, It is a massive, slow-motion pendulum swinging deep inside the planet.
And the rotation isn't the only thing shifting. The researchers also discovered that the inner core is actively changing its physical shape.
Yes, it is not the perfect, smooth, polished sphere that you always see in textbook diagrams,
Right, the near surface of the inner core is undergoing something called viscous deformation.
which is incredibly hard to conceptualize given the pressures involved. We just established that the iron forms a rigid lattice.
So how does it deform?
Over very long time scales, under millions of atmospheres of pressure and thousands of degrees of heat, solid iron can exhibit rheological behavior. It can slowly creep and flow without fracturing.
Think of it somewhat like silly putty.
Exactly. If you hit silly putty with a hammer, it acts like a hard solid and might even shatter.
Yeah.
But if you press your thumb into it slowly over an hour, it yields and deforms.
So what is pressing its thumb into the inner core to actually deform it?
The liquid outer core. The molten iron and nickel surrounding the inner core is highly turbulent. It is a churning ocean of liquid metal.
And the fluid dynamics of that ocean are constantly pushing and dragging against the solid boundary.
Over decades, that localized pressure physically molds the solid iron. The researchers mapped topographical changes, literal dents and ridges on the surface of the inner core that are over 100 meters high.
It is like a liquid river carving a canyon into solid rock.
Except it is molten iron carving a landscape into a superionic solid iron sphere.
Here's where it gets really interesting. Because you might be thinking, okay, a squishy, dented metal ball full of fluid carbon is spinning backward deep underground. Why does that matter to my daily life?
Fair question.
Well, it matters because the subterranean cycle is directly altering something you rely on every single day, the exact length of a second.
This phenomenon comes down to the fundamental physics of angular momentum. The Earth, as an entire system, must conserve its total momentum.
Like the classic ice skater analogy.
Right, a skater spinning on the ice.
Yeah.
When she extends her arms outward, her spin slows down because her mass is distributed further from her center of gravity. When she pulls her arms in tightly, her mass is concentrated and her spin speeds up.
And the Earth operates on the exact same mathematical principle to keep its total rotation balanced.
Yes, so because the Earth's core has been slowing its rotation over the last few decades and shifting its mass, the Earth's surface and mantle have had to speed up to compensate and conserve that total momentum.
Because the crust you and I are standing on is spinning just a tiny fraction faster, our literal days are getting shorter by fractions of a millisecond.
Which might sound completely inconsequential to a normal person,
Sure.
but it is an absolute nightmare for global timekeepers.
Oh, absolutely.
Since 1972, the scientists who maintain Coordinated Universal Time, or UTC, have had to step in and add 27 positive leap seconds to our global clocks.
Because historically, the Earth's rotation was gradually slowing down, right?
Over centuries, yes.
Yeah.
Primarily due to the gravitational friction of the moon pulling on our oceans and creating tidal drag. To keep our ultra-precise atomic clocks aligned with the physical rotation of the Earth, they occasionally had to pause the atomic clocks for 1 second to let the Earth catch up.
The script has completely flipped now. Because of the core's changing dynamics causing the surface to speed up, geophysicist Duncan Agnew recently published a prediction that we are heading toward a completely unprecedented event.
The need for a negative leap second.
Yes. Instead of pausing the clock to let the Earth catch up, the Earth is rotating too fast. We are going to have to skip a second entirely just to keep the atomic clocks aligned.
And that introduces a massive, unprecedented threat to our modern technological infrastructure.
Because computer systems absolutely hate time adjustments.
They are particularly vulnerable to time moving backward or skipping. Most global tech infrastructure relies on the network time protocol to keep everything synchronized.
And these systems use Unix time, which is basically just a continuous, ever-increasing count of seconds since January 1st, 1970.
The software is fundamentally programmed on the assumption that time only moves forward.
Right. If you add a positive leap second, a computer just sees the same second happen twice. It's confusing, but usually manageable. But a negative leap second means jumping from 11.59 and 58 seconds straight to midnight.
The 59 seconds simply never happens.
Exactly the problem.
Yeah.
Databases that rely on timestamps to order events like financial trading algorithms processing millions of transactions a second or airline booking systems would suddenly experience fatal logic errors,
A transaction might be recorded as happening before the event that actually triggered it.
causing infinite loops or massive data corruption. We already know how brittle these systems are. Back in 2012, when a standard positive leap second was added, it wreaked havoc. Reddit went down entirely. Netflix experienced massive outages.
Qantas Airlines had their entire booking and check-in software crash, forcing them to manually check in passengers.
It delayed hundreds of flights. And a negative leap second has never been tested in the real world. Tech experts fear it could cause catastrophic cascading failures across satellite navigation, telecommunications, and global financial markets.
But there is a massive twist to this timeline, and it comes from a completely different scientific discipline.
It's an important piece of the puzzle.
The data presents a crucial, impartial observation regarding how climate change is currently interacting with this tech crisis. According to the measurements, the melting of polar ice is actively delaying the need for this negative leap second.
How does that work mechanically?
As massive ice sheets in Greenland and Antarctica melt due to rising global temperatures, that meltwater doesn't just stay at the poles. The rotation of the Earth causes that immense volume of water to flow away from the poles and redistribute toward the equator.
It's the ice skater analogy all over again, but applied to the surface.
Exactly. By moving billions of tons of water mass away from the rotational axis at the poles and pushing it outward toward the equator, the Earth is effectively extending its arms.
Which inherently slows down the planet's surface spin. This surface-level deceleration caused by the melting ice is currently counteracting the acceleration caused by the inner core's shifting momentum.
Based on satellite gravity measurements, this massive redistribution of water has delayed the predicted tech crisis. Originally, geophysicists calculated we would need to implement the negative leap second by 2026.
But the melting ice has slowed the surface enough to push that estimate back to around 2029.
So what does this all mean?
Right. We have a dented supersonic core full of flowing carbon that is reversing its spin, altering the momentum of the entire planet, changing the length of our days, and fighting a literal tug of war with melting surface water. It's a lot to process.
It really is.
But the ultimate reason we need to care about this churning, chaotic engine is because of the invisible force it generates, Earth's magnetic field.
The magnetic field is generated by an incredible piece of planetary machinery called the geodynamo.
And what drives that dynamo?
It is driven primarily by the rapid turbulent churning of the liquid outer core, interacting with the extreme heat and rotation of the solid inner core. As the outer core cools, lighter elements are expelled, creating massive convection currents.
And as we learned earlier, that supersonic diffusion of carbon atoms zipping through the inner core's iron lattice acts as a vital thermodynamic regulator.
Exactly. It allows the core to cool slowly and keep those massive convection currents flowing steadily.
And thank goodness it does, because that magnetic field acts as our planetary cosmic shield. Without it, the solar winds, which are relentless streams of highly charged, high-energy particles constantly blasting out from the sun, would slam directly into our atmosphere.
Over time, that solar wind would completely strip away our ozone layer, boil away our oceans, and blast our atmosphere off into deep space.
If you want a stark, terrifying example of what happens when a planetary geodynamo fails, you just have to look at Mars.
Mars is the perfect example. It once had a liquid core and a global magnetic field. It likely had a thick atmosphere and liquid water on its surface.
But Mars is smaller than Earth, and its core cooled much faster.
Billions of years ago, its geodynamo shut down. Magnetic shield collapsed. The solar winds swept in, eroded the entire Martian atmosphere, and turned it into the freezing, irradiated barren desert we see today.
Earth's active geodynamo is literally the only thing keeping our planet habitable.
But just like the 70-year rotation cycle of the inner core, the magnetic field is not static. It is a highly volatile shifting force.
The North Magnetic Pole is a perfect example of that. When explorers first pinpointed it in 1831, it was located in the ice of northern Canada, but it has been drifting across the Arctic Ocean towards Siberia.
And the rate of that drift is accelerating dramatically.
Mm.
It used to wander at a leisurely pace of about 16 kilometers a year.
Now it is sprinting across the globe at about 55 kilometers a year.
Beyond just shifting poles, there are actual structural anomalies developing within the shield itself.
Seismologists and astrophysicists are closely monitoring a permanent weak spot, right?
Yes, known as the South Atlantic Anomaly. It is a massive depression in the magnetic shield located over South America and the southern Atlantic Ocean. In this specific region, the magnetic field is significantly weaker, allowing the Van Allen radiation belts to dip much closer to the Earth's surface.
While that weak spot doesn't really pose a threat to anyone walking around on the ground in South America, it is a massive hazard for space agencies.
When the International Space Station or any low Earth orbit satellites pass through the South Atlantic Anomaly, they are suddenly bombarded with much higher levels of intense solar radiation.
It regularly causes system glitches, corrupts data, and can completely fry sensitive onboard electronics.
Understanding the sheer resilience of this shield requires looking deep into the planet's history. A fascinating study from ETH Zurich modeled the thermodynamics of the Earth's interior from roughly 1 billion years ago.
And the crucial detail about that era is that the solid inner core did not exist yet. The Earth was still too hot. The entire core was a massive, completely liquid, metallic ocean.
Wait, if the solid inner core hadn't crystallized yet, and there was no freezing process to expel lighter elements and drive the convection currents, how on earth did the planet generate a magnetic field?
That is exactly what the researchers wanted to solve. They discovered that even without the structural anchor and the latent heat released by a freezing solid inner core, the sheer thermal convection of that fully liquid core was enough to keep the geodynamo running.
The massive temperature difference between the superheated center of the liquid core and the cooler mantle above it created enough churning movement to generate a highly stable magnetic field.
That ancient liquid-driven shield was incredibly robust. It was strong enough to block the intense space radiation of the early solar system, which provided the vital protection needed for early fragile forms of biological life to survive, evolve, and eventually spread across the surface.
It is just a beautiful continuous chain of planetary events that leads directly up to us sitting here today talking about it.
It is truly staggering when you step back and synthesize everything we've uncovered in this deep dive. The Earth's core is far from a simple dead ball of dense metal.
It is a highly dynamic supersonic engine. It relies on carbon flowing like a liquid through a rigid iron lattice to regulate its temperature.
It operates on a massive 70-year pendulum swing where its rotation pauses and backtracks.
Its surface is visually deforming, getting dented and molded by the turbulent molten iron oceans above it.
It shifts our planet's momentum so intensely that it alters the literal length of our days, threatening to crash our global technological infrastructure within negative leap second.
And most importantly, it powers the vital magnetic shield that intercepts deadly solar radiation and keeps our atmosphere from being blown into the void of space.
You realize just how deeply interconnected every single layer of the planet really is. Human activities and melting ice on the absolute surface of the crust are engaged in a literal, mathematically measurable cosmic tug-of-war with a molten supersonic iron ball 3,000 miles below ground.
And together they are dictating the exact millisecond precision of our atomic clocks.
Everything is tied together in complex webs we're only just beginning to map out.
This raises an important question, and it's a completely new angle we want you to consider as we wrap up today's exploration.
We've just discussed how the shifting of massive amounts of surface water due to melting ice caps is actively altering the rotational momentum of the entire planet, effectively applying a braking force to the Earth's crust that counteracts the deep core.
If human-driven climate changes continue to radically redistribute Earth's water mass over the coming centuries, changing the physical pressures and rotational dynamics of the mantle, could our actions on the very surface eventually influence the flow of the liquid outer core?
Could the redistribution of our oceans ultimately impact the long-term lifespan and stability of the geodynamo itself?
It is an absolutely massive, almost haunting question to mull over. Can we impact the very engine that keeps our planet alive?
We want to thank you so much for joining us on this deep dive into the center of the world. Keep looking down, keep wondering, and always keep questioning the incredible hidden mechanics operating right beneath your feet. Until next time.